We will start the second lecture of today's series. As for some of you who are new to this series, my name is Hendrata Dharmawan, and I'm one of the sponsors with Seed of Hope here. And today I'm going to talk about machine learning and data mining and its modern applications. Okay? Just another review of my background. It's mostly in the field of computer science and mathematics. My areas of interest is usually optimization and pattern recognition. Now, just to get a sense of the audience, how many of you have backgrounds in mathematics or sciences? What about engineering? Okay, good, yes. As we can see later, all of this machine learning approach should be able to help you with your respective areas of research. So, machine learning is a branch of artificial intelligence, and in a nutshell, is how we take a large amount of data and feed it into the computer, and we tell the computer to learn this data, and we are trying to mine, to extract information from this raw data, right? And hopefully we can get better predictions about future data. That's why it's called machine learning. The machine has to learn from this data. It has a lot of wide areas of application, but first I want to show you this latest development of Google AlphaGo. How many of you guys here know the game Go? Oh, good number, yes. It's a very complicated game, but maybe because before that I want to compare it to chess, the game of chess. In 1997, IBM Deep Blue beat Garry Kasparov, the then world champion in chess. Right? This is Garry Kasparov, and this was the Deep Blue. Right? And at that time, no Go program can defeat a human professional. That much Go is much more complicated than chess. In 2011, IBM Watson won Jeopardy. How many of you know what Jeopardy is? Right? Yeah, it's a trivia show. It's a TV show usually based on trivia in the US. These are the really reigning champions, the ones who have won a lot of Jeopardy shows. And this is IBM Watson, and it won. And at that time, it was considered a major success in the field of machine learning. And just a few months ago, Google came up with this software called AlphaGo that can beat Fanhui, the European Go champion, 5-0 in October. And just last month, it beat Lee Sedol, the second-ranked Go player in the world, 4-1. And this is an example of a Go game in progress, right? Deep Blue, while it's a very smart machine, it's not machine learning per se. It's a very sophisticated chess program, but a lot of grandmasters helped in the development of Deep Blue. It tries to tell Deep Blue, do this and don't do that. It's trying to bake in their tactics, and then Deep Blue uses its massive computing power to see a lot of moves ahead. But AlphaGo is very different in its approach. Right? All it knows is just the rules of Go, which is not very complex. And it watches other people play Go 100,000 times from the internet, and then it plays against itself 30 million times in isolation. And the point here is that when you play against yourself, one of you will win and one of you will lose. Both sides learn from its mistakes. What move did I do that I lost this game? And for the side that won, what did I make? What did I do such that I can win this? And it continues to learn from the games, the 30 million games that it plays against itself, right? And the point here is that this can be extended to other games, such as backgammon or tic-tac-toe. All we need to do is to program in the rules of backgammon. You don't need to change the strategy or what are the common sense things to do in backgammon. It needs to only know the rules, and it will play against itself many times, and suddenly it will be a good backgammon player, right? And this is basically the spirit of machine learning, the machine that continues to learn itself. The outline of this presentation is I'm going to show you some examples in different areas of what people have done in the past, and some of the basic techniques on how to do these, and some of the dangers of over-learning or overdoing your machine learning. So the first one is this breast cancer prognosis program from University of Wisconsin. What we have here is more than 500 patient records with breast tumors. And for each patient, we take these measurements, radius, texture, perimeter, and so on and so forth. Each patient is known to be benign or malignant, right? And we feed all of this data into the computer, and we tell the computer to try to learn the difference. Right? Now, the question is, can the computer tell if there's a new patient and we know her attributes? Can you tell if this patient is malignant or benign? Right? And turns out we can, with 98% correctness rate. Or it drops to 90% rate within lifetime, because some patient who's benign develops cancer later on. Right? But that example highlights how machine learning usually works. We view our data, the patient data, as points in n-dimensional space. In this case, n is 32. Right? And each point has a known label. Are you benign or are you malignant? And then you feed all of this data into the computers. And then for a new sample point, for a new patient record like this, you output your best guess. Is this patient benign or malignant? Right? And then later, when we learn that our prediction was right or wrong, we update our program. The computer learns from its own past success or past mistakes. Right? That's why it gets better over time, and that's why we call this machine learning. Right? Other applications in healthcare using techniques similar as the breast cancer one is appendicitis, heart attacks, diabetes, hyperthyroidism. And what I want to highlight here is that even for the case of hyperthyroidism, we have 3 examples of 3 different classes of patients. So it's not just A or B. It's not just acute or not, but we can have 3 different labels here. And of course, there are a lot more research going on in different areas of application. Another area of application is handwriting recognition. We have a large number of training samples like this, and for each of these images, we take measurements of aspect ratio, pixel distribution, distance, curvature, and then we know the labels of these characters. Right? We know this is a 7, this is a 2, and then we tell the machine to learn the difference. And then we have to combine it with techniques such as digit splits. For example, when you see this image, we have to tell the machines that these are 5 different numbers. It's not one single number. So you can be split into 5 different numbers. And sometimes handwritten language, handwritten letters can be very ambiguous. For example, in Roman alphabet, lowercase a and lowercase d, when it's handwritten, might be very close, right, depending on the length of your stem. How do we distinguish whether it's an A or D if it's kind of borderline? We can look at the spelling context. What are the letters that come before or after in that word? Or you can also look at the words that come before or after that word in the whole sentence. And hopefully the language understanding can help us understand what's the intent of this writer, right? Other applications in computer vision or hearing is speech recognition. For those of you who have a smartphone, Siri, Alexa, Cortana. Facial recognition. If you have uploaded a picture to Facebook with your friends, and then sometimes Facebook will suggest, is this your friend? And and a lot of times they get it right. And that's also machine learning. Sign language recognition. For the hearing impaired individuals, when the speaker is performing sign language, you can take a video of the speaker, and then you can give it to the computer, and the computer can translate that video into English. Satellite imaging for the different types of soil, right, whether it's fertile or not, how good this is for farming. For sonar vision, whether we're looking at mines or rocks. Right? There's another example that I didn't mention here, but self-driving cars that you might have heard being very popular in the news recently. But self-driving cars is also heavy applications of machine learning because it really has to look at the road and know what it's looking at. There's another example from my research, my master's thesis at MIT. It's called Emotion Recognition Program, where the input is the speech waveform of the trained actors. So we pay the actors to speak in a very angry or joyful way or sad way. And we're trying to distinguish, is he calm or excited? Or is he pleased or displeased? And that tells us whether it's happy or joyful or angry or sad. And turns out we can perform better than human for low excitement samples. So we can distinguish between sad or happy in a very calm way. Right? Another example, glass identification. So we have hundreds of examples of glass shards, and we take measurements of refractive index and different chemical content. And we know that this glass is from building, vehicles, containers, tableware, or headlamps, right? And then we use the computer to train all of these samples, and turns out we can tell a new given sample with 75% accuracy. And you can imagine that how this is useful in criminology and forensic science. If you find a glass shard in a crime scene, then you know, is it from a window or for a vehicle, right? Another example, wine identification. So given samples of wine, then we analyze its chemical content, and we can tell with 100% accuracy 1 out of 3 grape strains in Italy. Now, I did my research and I found out that Georgia has 38 different strains of wine. So I would like to try this technique on the Georgian wine data and maybe see how it performs. Right? Now I'm going to show you how do we do all of those examples. And one of the most basic technique that you do is called K-nearest neighbor. So what you have here are your red samples, right, and the blue samples. And the green dot here is your new sample that you want to find out. Is this a red or is this a blue? You take your K nearest neighbors, in this case K is 3, so you take the 3 nearest neighbors, and you take voting. There are 2 B's among the nearest neighbors, and there's 1 A. So this is probably a B, and that's our guess, B. Right? It sounds very simple, but it's surprisingly powerful. This is another example where we have our black dots, our black samples, and our red samples. And for every single point in this chart, we perform the K nearest neighbor. In this case, K is also 3. Right? And if it's a red, then yeah, and if it's a black, then we label it black. And this green line represents where the boundary happens between red and black. It's 0.5 because sometimes you're equidistant. Your 2 nearest neighbors are exactly the same distance, so you're not sure which one. So that's why we put it 50-50 guess here, right? And as you can see, even for such a simple technique, it can separate the black and the red pretty cleanly. And this simple technique has a lot of powerful applications, such as this handwriting recognition that I mentioned earlier. We have 60,000 images like this, and when there's a new query, we find its nearest neighbor, and then we know it's a 4. Right? Similarly, sign language recognition. So we have a lot, hundreds of thousands of images of these gestures, and for new query, we find its nearest neighbor, and then we know it's this kind of gesture. And that's how the computer were able to translate the video into English. Early facial recognition. This is what a lot of the social media uses pre-2007. For each new picture that you upload, it takes a lot of measurements such as the width of your eye, of your nose, right? Like the height of your nose, the size of your lips, and so on and so forth. It takes all of these attributes, right? And then tries to find among your existing friends who is closest to this new picture that comes. And turns out, yes, you can tell it with a high degree of accuracy. And I said early, because starting 2007, Facebook changed its algorithm to a different technique that is much more powerful. The next technique that I'm going to show is called neural network. It's called neural network because it mimics the network of neurons in our brain. So this is a picture of our brains from the close-up, and every single one of these is a neuron. And this is a picture of single neuron. It has these things called dendrites, which are receptors from different neurons, and it takes electrical signals. And if there are enough signals being sent, then, and the signals surpasses a certain threshold, then it activates and sends electrical signal to this axon, and it goes to another neuron, and so on and so forth. Each neuron receives inputs. So this is the computer model of each neuron in our machine learning program. The inputs are given numerical weights, and we're giving it a sum. We're taking the weighted sum of the inputs, and we compare it to a certain threshold. And if it's higher than that threshold, then we fire a signal to the next neuron. Now, these weights and this threshold, those are the things we want to learn. Those are the things the machine learning algorithm needs to find out how to predict your output most effectively, right? This is an example of neural network where every single one of these circle is a neuron that I showed before. So as you can see, for this neuron, it receives inputs from the following neurons, right? And it sends outputs to a lot of neurons. And typically we have 3 layers: input layer, hidden layer, and output layer. And these 3 layers are usually good enough for most practical applications. And the final output of your output layer, this is what the machine guesses, right? This is another example of neural network in action. Now, don't worry about the many numbers here. It looks complicated. But the point I'm trying to make here is that there are these weights on each edge. And these are what we're trying to learn. And for each given input, we take the weighted sum of these weights, and we compare it to this threshold. And if it's sufficient, if the input is high enough, then we fire and we send events to the other neurons. And then these other neurons compare it to its own threshold to compute this final output, right? And how do you learn the weights and the threshold? That's the algorithm that we call backpropagation algorithm. For new training point, as I said before, we compute the predicted output. Now, we compare this output to what we know about that output. So we know it should be this much, but your output was this much. So we take the difference and we try to update these weights accordingly, right? So we reward the neurons that got it right, and we punish the neurons that got it wrong, right? So we go back 1 layer at a time, starting from output layer. In this case, given this difference and this difference, we update these weights and these thresholds to try to match more closely. And then remember that these weights affect the output of these neurons. So given these weights, we update these weights and this output. And then we keep going back 1 layer at a time. And that's why it's called backpropagation, right? And after we reach the first layer, we come back from the very beginning and we continue to rinse and repeat, do it from front layer to back layer many, many times. We repeat it until the performance is satisfactory. For example, if we can distinguish the data for 100% of the time, or if your weights and thresholds don't change that much from one iteration to another. So that means no matter how many times you run it, it's not going to change much from now on. This is as good as it's going to get, right? Now, I showed you the early facial recognition technique earlier, but this is the modern facial recognition that Facebook uses. In that case, they used many layers and not just 3 layers. And it turns out that each layer, each neuron within the layer, they're responsible for one specific feature of the face. For example, does he have a thick eyebrow? Does he have a big nose? Does he have a thin lips? And does he have a big ears? And so on and so forth. All of those neurons are responsible for detecting just the thick eyebrows or just the high nose, right? And when you compare it to your known sample of your friends, then it can output it. This is so effective. In fact, Facebook boasts a 97.25% accuracy. It's only slightly worse than human, 97.53, right? And this is also the technique that I used in trying to recognize emotions from the wave file that I mentioned earlier. We have no knowledge of the language context, so we don't know what the person is saying, or we're not trying to do any speech recognition in that way, but really just recognizes emotions. And we are using the technique called dynamic Bayesian network, which is a generalization or a variant of neural network. And our network looks like this, except it's not just one, but we have many of these repeated, and they're all connected as well. And it's not just 2 of these, but they're all repeated many times within a single structure, right? I'm just showing 2 for simplicity. The top layer here, as I said before, usually one neuron is responsible for each feature, and we found out that it turns out the top layer is responsible for each phrase. Within your overarching phrase, how is his intonation and his inflection changes within the whole sentence. The second layer is responsible for the word level. For example, your breathing or the pauses that you take between words, or the pitch change between each word, right? And the third layer is the phonemes, or each syllable. How is your tempo changes from one syllable to another, or your pitch, or your plosiveness. Plosiveness is like that sound, right? How does it change, or how does it vary from one phoneme to another? When we measure all of that and we try to use the generalized version of backpropagation algorithm, we learn that we can predict where the speaker is in this quadrant. Are you displeased or are you pleased? Where in the spectrum do you fall? Or are you calm or are you excited? And where in the spectrum do you fall, right? For example, this speaker might have been excited and displeased, so he's angry, right? So if you're here, you might be, or if you're here, you might be happy, like pleased in a very calm way, right? So we try to distinguish between all 4 of these emotions. And it turns out we can achieve 70 to 80% recognition rate. This is still worse than our human benchmark recognition rate. But still, we can perform better than human for the low excitement samples, such as between being very depressed or being very happy in a calm way. Right? Turns out human recognition is almost 100% for high excitement. If you're very angry and you're very joyful, turns out humans can recognize it for 100% of the time. And the machines have a harder time distinguishing. Right? And we find out that Spanish, Signal, and German are easier to detect using this emotion recognition technique. We don't know why that is. Maybe there's a feature of the languages themselves that maybe part of the language causes you to speak a certain way when you're angry. Right? Of course, there are a lot of improvements that can be done, and it can warrant further research here. Now, the third technique that I'm going to show you is called support vector machines. So in this chart, you have the red samples and the blue samples here. And we are trying to find a line that separates the blues from the reds. Right? This line here separates the blues from the reds cleanly, but we like this line better because it has a higher margin. So what is the point of coming up with this line? The point is, you have a new sample. Let's say your new sample is right here. And this is the line that I come up with, my separator, and my new sample is here. Then I think, okay, so it's on the same side as my line, as the reds. So I guess that this is the red, right? Likewise, if your sample is here, then you think, okay, this is the blue. This is why the angle of the line is important, because if the point is here and we chose this line, then it would have been classified as the red. But visually, we kind of think that this belongs more with the blue. That's why we choose the line that has the maximum margin of separation. But what if your sample is not linearly separable, such as this example here? You have the greens and the reds, and there's no single line that can separate it cleanly. Right? So your standard support vector machine doesn't work. But then you use kernel functions that maps your input space to feature space. What it means is that you apply any of these functions to these points, and you come up with this new picture, right? And now you can see that these points are linearly separable, and you can come up with this a clean line of separation. Now, you take the inverse of these functions, and you map it back to the input space. So you apply it here, and you take it back. So these are your training sets that are the same as this, but your line now becomes a curve, because these functions are nonlinear, right? And as you can see, this curve cleanly separates the greens from the red. Right? The point I'm trying to make here is that you can come up with any functions you want. Exponential, logarithms, sine, and cosine. Anything that's nonlinear may help you separate your points cleanly, even if it's not a straight line. Because in the feature space, after you apply this function, it becomes a straight line, right? This is another example of support vector machines where you have the blue and the red dots. And we have this green curve that's kind of cleanly separates, but it misclassifies a little bit, right? There's still some blues here that are misclassified, and there's still some red that are misclassified. But as you increase your kernel functions better and better to higher dimensional power or to higher complexity, you can always separate it cleanly. For example, the green curve here, it separates the blues and the red cleanly, right? Now, if I ask you a question here, which one is better? The green ones or the black ones? The simple parabola or the squiggly ones? The squiggly ones? Right? Anyone think the simple parabola is better? All right? It's simpler, right? So which one do you choose, the simpler or the 100% recognition rate? Right? Actually, we already are getting two different opinions here. The answer is the better classifier is the one that are performing better in the real world. It could be this one or it could be the green ones, right? We have to test this in the real world. Remember that I said for each new patient that comes in, it learns from its mistakes. And that's how you tell that, yes, this is better or this is better, because it's actually tested in the real world. And the whole point of machine learning is to help your new patient know if she's benign or malignant, right? So it is hard to say without knowing what this data is, which one is better. It could be the squiggly ones, it could be the simple ones, right? The problem is we don't have the real world in our data set yet. What I have is this 500 or so patient records. Now, how do I choose which one to how do I choose which of these curves to use, right? The technique called cross-validation. What you do is you split your data set into 10 different buckets of equal size, if you will. And you save one of them, right? You don't touch it. And you use the other 9 to train your classifiers until you're satisfied with the performance, right? Now, after that's done, you take your classifier and test it on number 10. Right? That's the closest example. That's the closest approximation on how it will perform in the real world. Right? Because this classifier has not seen this data set number 10 before. So this is another example that the squiggly line is sometimes better, it's not always better, simpler, right? It can be better, but it still misclassifies. And it's really related to the complexity of your kernel functions, right? Now, there's the plot here where this x-axis is the number of iterations you do, or the complexity or dimensions of your kernel functions, or any measure of complexity of your classifier. And this axis is the error rate, how much it misclassified. This training set is your 9 buckets that I mentioned before. And as you're running your classifier, as you're training it more and more, it will go down. Of course, it will go down because your algorithm is designed to reduce the misclassification rate. Right? But how does it perform on your data set number 10? That is the question. At first, it will go down because your classifier is actually getting better. But after a while, it will go up. Now, what is happening here? Right? What happens here is your classifier is really finely tuned to your 9 sets. It's really sensitive to the 9 sets, and it's really specific. It's custom tailored to the 9 sets. This is where you see that really squiggly line here. But does it mean it performs better in the real world? Probably not, because when you try it on the data set number 10, then it increases, it has a high error rate. So when you see this plot, then you know this is the point where you should stop and take that classifier here and deploy to the real world. And of course, you are not doing this only once, but because you have 10 different buckets, so you can rotate in which one is the testing set and which one is the training set. And you can do this 10 times and take the average. So this plot is more like the average of 10 runs, right? The average of 10 testing, right? Now, after you've seen all the three basic techniques that we've used, I'm going to explain some of the recent advances that people have done in the field. There's this trend called deep learning neural networks, where it's the neural network that I showed before, except you don't have 3 layers anymore. You have 15 or even 20 layers. Right? It tries to truly mimic the human visual cortex. For example, when I come to the room right like this, I know that's a chair, I know that's a table. I've never seen that particular chair before in my life, but I know it has 4 legs and it has this back part, and right away I know there are features that are usually associated with a chair. And human brain works that way. And we are trying to mimic that. Remember when I said each neuron is responsible for each feature? So this tries to really mimic how the human processes visual information. And why is it only popular recently? Why is it not done earlier? Because it's really expensive to compute. Right? Your running time grows exponentially with the number of layers you have, and it grows quadratically with the number of neurons you have in each layer. So it's huge complexity, and it's only possible as we have come up with faster and faster hardware recently. There are improved algorithms. The backpropagation that I said earlier, that's the most basic version. But if you can exploit certain structure of your neural network, you can improve the algorithm to not be as brute force. And training data. Of course, only recently do we have such a huge amount of data to train. Because if you don't have enough data, your classifier is not going to be very good, and therefore it's not acceptable. Right? And then expert systems. This is another trend that people are trying to do these days, where you don't use just one context, but you use a lot of context to guide our guesses. In the handwriting example that I mentioned earlier, sometimes to distinguish between an A or a D, or a B and a P, you look at the letters around that letter within the word, or the other words within the sentence. And your knowledge of the grammar of that particular language, right, or what words are possible, like the spelling or dictionary of that language, should help you distinguish. Right? Or, for example, in my emotion recognition research, one of the things we were going to try next is to combine it with other contexts, such as the language. If we can tell what the person is saying, maybe we can tell whether he's angry or he's happy. Right? They usually contain very different words. Or if we can get an example of the video of the person who's speaking, and then we have some visual context to guide our guesses, maybe we will perform better. Right? And the other major push is speed improvements, so that we can do our guess, we can perform our guess on the spot. Right? How many of you have shopped online before in an online store? A lot, right? And usually websites such as Amazon gives you a suggestion. Customers who have bought the things that you did in the past usually also looks at these things. Right? Those are all machine learning. But it's impossible to do it if your algorithm is too slow. It's too late to suggest things after your customer closes the window. So it has to be really fast. Right? And that's why people are trying to improve the speed. So by now, as you understand how machine learning techniques can be used in different areas, as I saw before, there are a lot of you who are majoring in different areas of sciences. Machine learning may aid the data analysis in your respective areas of research. The beauty of it is that people have done all of the dirty work, for example, to do all of these toolboxes, and they're publicly available in MATLAB, and they're free too. There are a lot more algorithms than we talked about, and each algorithm is very specific for each kinds of data. You don't need to know how they're done. All you need to do is feed in your data set and feed in your known labels and run it, and then you get your classifier as an output, right? It's really easy to use. But if you're still interested to learn how it works underneath, there are machine learning conferences and there are online forums that can help you. There are also machine learning contests being done regularly. So there are a lot of young aspiring machine learning specialists who are willing to do this for free even. They will take your data set and perform the data analysis and say, give it a try. Maybe this can help you. Right? What do they get in return? They get to practice their skills, and they also get some credibility back. Or if you want to practice yourself, these forums also have free data sets available. All of the healthcare examples that I mentioned before, they're available online if you want to try to do those yourself. Right? So either you can try to become a data scientist yourself, or you can outsource your pattern recognition problem to other data scientists. So I would like to conclude this lecture by giving special thanks to International Black Sea University for inviting us, and for the Seed of Hope for arranging this lecture series. Thank you.